All right, guys. So in this video, we are going to talk about the ideal gas law. All right. So this gas law is slightly different because it's only got, as compared to the combined gas law, there is only one set of variables. So nothing is changing in this one. All right, so we are either trying to find volume, pressure, or temperature of a given amount of mass under stated conditions. So nothing is changing. And our equation is PV is equal to nRT. So you guys should know that P stands for pressure, V stands for volume, and T is temperature, which still, as always, must be in Kelvin. One thing I do want to add, though, is that your volume in this one must be in liters. All right, so in the last one, it didn't really matter as long as you had the same volume, but this one it does. All right, so temperature must be in Kelvin, volume must be in liters. Okay, guys, and then we have some new variables. So the first one is N, and it stands for number of moles. Yay, moles are back. I don't know, you guys probably already saw moles, but anyways, moles. Yay. And it just says you can substitute moles divided by molar mass for this, essentially, which is basically just doing the conversion in the problem instead of doing it after the problem. Then our other new variable that you guys probably haven't seen before is, of course, that R value. And R is the universal gas constant. Okay, so it's a constant. It's on the formula chart, but I'm going to go through it with you guys real quick. So R can have several different values. So it can either be 0.0821 liters times atmospheres per mole, divided by moles times Kelvin, 62.4 liters times millimeters of mercury divided by moles times Kelvin, or 8.314 liters times kilopascals divided by moles times Kelvin. So guys, we have these three different R values, all right? And basically we have to choose which R value we use based on the one thing that's different in their units, and that's the pressures. So like in our first one, it's liters times atmospheres. So if we're in atmospheres, that's the R value we would use. Next one is liters times millimeters of mercury. So if we're in millimeters of mercury or torque, so on the same scale, that's the one we would use. And then finally, our last one is for kilopascals. So those are going to be the three R values. And I always say it's kind of like ice cream. You have to match your ice cream to your topping. So we have to match our R value to our pressure value. They have to go together. All right. So this equation's pretty easy because it's only one set of variables. So when we go through our problems, we're going to label the different variables in our problems and then plug it in and solve it. All right. So our first problem says how many moles of oxygen must be put in a 500 milliliter flask at 20 degrees Celsius to have the pressure of the flask of 1.77 atmospheres. Okay, so let's go ahead and label all of our variables and figure out what we are looking for. So the first thing it says is how many moles of oxygen. So that would be N, all right? And that's our unknown. So N is like a question mark or X, whatever you want to say. Must be put in a 500 milliliter flask. That's our volume because we're in milliliters. Now guys, remember I said it has to be in liters. So you can do your real quick conversion. So King Henry died by drinking chocolate milk. All right, we're in milliliters. Want to be in liters. 1, 2, 3 to the left. So 1, 2, 3. So that would be 0.500 liters. At 20 degrees Celsius, there's our temperature. But again, we must be in Kelvin. So we'll add 273 to that, which gives us 293 Kelvin. And then finally, last value that we see is 1.77 atmospheres, which is our pressure. So you guys can see we have P, V, N, and T. The only one we're missing is R. It's a constant, so we have to plug it in from our equation. Since my pressure is in atmospheres, my R value that I'm going to use is 0.0821. Okay? So now I'm going to go ahead and take my equation. So PV equals NRT. RT. I'm solving for N, so I'm going to manipulate my equation so that N is all by itself. All right, so in that case, that means I'm going to divide both sides by RT. So we get that N is equal to PV divided by, oops, if I can write, RT. All right, and we'll just plug it in. So my pressure is 1.77 atmospheres times my volume is 0.500 divided by my R value, which is 0.0821 divided times my temperature, which is 293. Now, guys, you're going to plug this into your calculator. I do want to caution you guys that when you plug it in, to make sure that you put the bottom all the way in parentheses, or else you'll end up with some bad math. A lot of you guys have also reached out and been like, how do we do sig figs for like gas laws? And guys, it's really easy. It's just the fewest number of sig figs overall. So like my first number has 3. Second number has 3. This one's a constant, so we wouldn't count that. That one has 3, so my fewest number is 3. So my answer should have 3 sig figs. So that would give us 0.0368. And then don't forget your units, which is moles. Boom. That's it. That's the ideal gas law. Not so bad. Okay. Let's do another one. All right. And if you guys noticed, when I went through, I kind of went ahead and the first time I read through it, I underlined all the variables or highlighted all the variables and then went back and labeled them. So I would highly encourage you guys to do that as well. All right. So first things first is it says if 1.17 grams of helium are put into a 5-liter container at 10 degrees Celsius, what would be the pressure in the container? And then it does tell us in torr. All right. So first things first is I have that 1.77 grams of helium. So it's in grams, but I can convert it to moles. So that's going to be my N value, and I'm going to convert using my molar mass because I know it's helium. So I'm going to convert using my molar mass to a 5-liter container. That's volume at 10 degrees Celsius. So again, it's temperature, but we need to add 273. So that gives us 283 Kelvin. And then what would be the pressure? So we want to know pressure. And again, we want to know in torr. All right. So the only variable that's not in our problem, once again, is the R. All right, guys. And so we need to figure out which R value to use. Like I said, millimeters of mercury and torr are on like the same scale. So we would use the same R value for them. So we're going to use 62.4 as our R value here. All right. So first things first, I am going to convert my grams to moles. So if I have 1.17 grams of helium, using my molar mass from the periodic table, 4 grams of helium is 1 mole of helium. Plug that into your calculator and I get 0.293 moles. Just for the sake of space, I'm going to manipulate my equation just in my head. So sorry, guys. But we have PV equals nRT. I want pressure all by itself, so I'm going to divide both sides by volume. So I end up with P is equal to number of moles times our ideal gas constant times temperature divided by volume. We'll just plug everything in. So my number of moles is 0.293 times my ideal gas constant, which is going to be 62.4, times my temperature, which is 283, all divided by my volume, which is 5. Plug it into your calculator. Once again, our fewest number of sig figs is 3, so my answer should have 3. And I got 1,030 torr for my answer there. All right. Last one for this ideal gas law. Last one for this kind of version of the ideal gas law. And then we're actually going to talk about another version of the gas law, ideal gas law as well. All right. So it says, what is the molecular mass of a gas if 20.6 grams of it in a 500 milliliter container exert a pressure of 2,500 millimeters of mercury at 350 Kelvin. Okay, so first off, our problem is asking for molecular mass. All right, I'm going to tell you guys this problem is a little bit different than what we've been doing. It's the same idea, but real quickly, I just want to go ahead and kind of give you guys a definition of molecular mass. So molecular mass, is equal to the mass divided by however many moles, right? The molar mass is the mass of 1 mole. So if I wanted to figure out basically the molecular mass of a substance, I could say, well, what's the mass of that substance and then how many moles are in that mass, and I can get the molecular mass that way. So we are going to use this eventually, that 20.6 grams, but we're actually going to wait till the end. So what I'm going to end up doing is I have right here 500 milliliters, that's volume. So again, need to convert it to liters. So move our dot 3 times to the left, end up with 0.500 liters. Then we have pressure and we have temperature. So guys, we can solve for number of moles here. So we can solve, we don't know what N is. We can solve for number of moles and then use the mass in the moles to figure out the molar mass. Okay, so the only thing we're missing here is our R value. We have millimeters of mercury, so we're going to use our R value that has millimeters of mercury in it. So that is going to be 62.4. All right, so then once again, for space, I'm just going to manipulate my equation. So N is equal to PV divided by RT. And then we're going to plug everything in. So 2,500 times 0.500 divided by my R value, 62.4, times my temperature, which is 350. Okay, should have 2 sig figs in our answer there because 2,500 only has 2 sig figs. So I got 0.057 moles. All right. And so then I can plug that into my mass divided by moles equation. So I have my mass is 20.6 grams divided by my moles, which is 0.57 moles. And I got 360 grams per mole as my molar mass. I got 361, but since this only has 2 sig figs, I would say that one only has 2 sig figs, so I got 360 grams per mole.